Hi again, students. Today we're going to learn about the energy associated with capacitors. You see, when we connect a battery to, the two plates of a capacitor, a certain amount of energy gets stored in it. Where does this energy come from? And what's exactly the value of this energy stored in the capacitor? And some work is done by the battery in charging a capacitor. So, what is the work done by the battery in charging a capacitor? All these are complicated terms, aren't they? But we are going to learn about all these things in this chapter, the energy associated with capacitors. So let's proceed. First of all, let's learn about the work done in charging an object. You see, the work done in charging an object is the same as the potential energy of an object, isn't it? So by studying the work done in charging an object, we'll get a clue about the potential energy of capacitors. Let's say there's this object of potential V and dq charge is coming and this object is getting charged. So what will be the work done in charging this object you see on your screen, this silver red one? Clearly, the net work done in adding a charge dq to this object will be equal to the change in the potential of the charge dq into the charge dq, isn't it? After all, the work done in moving a charge dq from infinity to a particular point A is clearly dq into VA minus V infinity, isn't it? In this case, VA is V, the potential of the object, and V infinity is 0. So dq into V is the work done in moving a charge dq from infinity to the surface of an object, isn't it? So we can calculate the net work done in moving, the entire charge of this object from infinity to the body by integrating dw. W is clearly integral V dq. Now if we replace this object with a capacitor, what will the value of V be? We know that the potential difference across a parallel plate capacitor is always Q by C. And that means that the net work done in imparting a charge Q to the plate of a parallel plate capacitor is integral Q by C dq, isn't it? And if that is the work done, the value of the integral gives us the value of the total work done, that is Q square by 2C, isn't it? So Q square by 2C is the net work done in charging a capacitor from 0 charge to a charge Q, isn't it? Q square by 2C can also be written as half CV square or QV by 2. You see, in this term Q square by 2C, you can take out Q by 2 and have Q by C in the middle. Now Q by C can be replaced by V. So this term becomes QV by 2, which is the same as this term here. Similarly, QV by 2 can be multiplied and divided by C. And again, this Q by C here becomes V. And so this term becomes half CV square. So all three forms of this expression are generally used to represent the net work done in charging a capacitor. Understood? Now this work done is the same as the potential energy stored in a capacitor. If you remember the definition of electric potential energy, it is the net work done in bringing the charge in a charge system from infinity to that point. So the net work done in bringing a charge Q from infinity to the plates of a capacitor will be the potential energy stored in a capacitor, isn't it? After all, that's the definition of potential energy. And that means that this expression that you see on your screen, Q square by 2C, half CV square and QV by 2, these expressions are not just expressions of work done in bringing a charge Q to a capacitor. They are also the expressions of potential energy of any capacitor in general. Understood? And these expressions are true for all capacitors, spherical capacitors, spherical shell capacitors consisting of two terminals, all capacitors, because V equal to Q by C is always true in general. Understood? So that was about the potential energy stored in a capacitor. The next term we are going to study is the energy density in a capacitor. Do you remember what energy density is? Well, I had talked about this phenomenon when we had talked about electric field. Energy density is basically the electric energy per unit volume stored in an electric field. This means it is the net potential energy of all the charges that are stored in an electric field per unit volume. So for example, if we consider this volume here, in that case the energy density per unit volume here will be equal to the potential energy of all the charges that are present inside this volume per unit volume. So if you take any 1 meter cube of volume or free space and you calculate the net potential energy of all the charges that are stored in this 1 meter cube of volume, you get the net energy density of that particular volume. Understood? We had already discussed this phenomenon in the chapter electric field. In that very chapter, we had also discussed that the net energy density formula is given as half epsilon naught E square, where E represents the electric field because of all the charge configurations present in a certain volume. So if we want to calculate the energy density in a capacitor, the formula will again be half epsilon naught E square. Now we know that electric field inside a capacitor between the plates of a parallel plate capacitor is sigma by epsilon naught. So you can calculate the energy density between the plates of a parallel plate capacitor, by putting sigma by epsilon naught here. The energy density between the plates is half epsilon naught into sigma by epsilon naught whole square, isn't it? We can even derive this expression, using our fundamentals of physics. For example, inside the capacitor, the energy density is clearly du by dV, energy per unit volume. We can write that as U divided by volume, that is potential energy of the capacitor divided by the volume between the plates of the capacitor, and that can be written as half CV square divided by AD. Now when we substitute the value of the volume of the capacitor as AD, the capacitance of the capacitor as epsilon naught A by D, and when we substitute V, the potential between the two plates of the capacitor as E into D, we get the final value of the energy density as half epsilon naught E square. So we can very simply derive this formula also, but half epsilon naught E square is the formula that you must remember. The next concept we are going to study is related to charging a capacitor using a battery. You see, a very interesting thing happens when we charge a capacitor using a battery. We've always seen this symbol of a battery connected to the two plates of a capacitor. But what exactly does the battery do to the capacitor? Like, what happens when you connect a capacitor to a battery? A battery is basically like a pump. What it does is that it charges a capacitor by taking charge from one capacitor plate and putting that charge in the other capacitor plate. And that is the reason you always have opposite charges on the plates of a capacitor, plus Q on one side, minus Q on one side. That's because this battery takes Q charge from this capacitor plate and puts it here on the other capacitor plate. So you can imagine, how the battery transfers electrons from one capacitor plate to the other capacitor plate. Like this. So this is the important concept that you must remember. Whenever two plates are connected to a battery, or whenever any capacitor is connected to a battery, all the battery does is that it acts like a pump. It takes electrons from one terminal and transfers them to the other terminal. And that is the reason why all capacitors connected to a battery will always have equal and opposite charges on each of their terminals. Understood? This is an important phenomenon and you must remember it. Even in the case of a spherical shell capacitor, in the very last chapter, we had studied that when we earth the middle shell, this inner shell, and we give a charge plus Q to the outer shell, in that case, the electric potential of the middle shell becomes zero. We had studied this phenomenon in our last chapter. However, in that case, by equating the electric potential of the middle shell because of the outer shell and because of the inner shell to zero, we had finally got the value of the charge on the inner shell as minus QA by B. If you don't remember it, you can obviously, go back and watch that portion of the video again. It's there in the last chapter. The essence of what I'm saying is that when you earth the middle shell in a spherical capacitor, the inner shell gets a charge minus QA by B. However, when you actually connect the spherical capacitor to a battery, the charge that the spherical capacitor gets is plus Q and minus Q. So what I want to say is that no matter what kind of capacitor you connect to a battery, the two terminals of the capacitor will always get a charge plus Q and minus Q. They will not get any other charge except for equal and opposite charges. Understood? In fact, even if you reverse the terminals of the battery, in that case the charge will be reversed and the outer shell will now get minus Q charge and the inner shell will get plus Q charge. Note that this was not the case, when you imparted a charge plus Q to one of the shells and when you earthed the other shell. In that case, you get different charges which you have to calculate by equating the potential of one of the shells to 0. Understood? So well, we can even calculate the potential difference in the case of a spherical capacitor when a battery is connected to each of the spheres. For example, the electric potential of the inner sphere will clearly be minus Q by 4 pi epsilon naught A plus Q by 4 pi epsilon naught B, isn't it? Similarly, the electric potential of the outer shell will be minus Q by 4 pi epsilon naught B plus Q by 4 pi epsilon naught B, isn't it? Well, ponder carefully and you'll get these potential values. So the net electric potential difference between the inner and outer shell in case of a spherical capacitor connected to a battery will be Q by 4 pi epsilon naught into B minus A by AB. This will always be true even if you reverse the terminals of the battery. Understood? You must remember this expression, for use in objective type questions. The capacitance of a spherical capacitor when a battery is connected to it will be plus Q by V, the charge provided by the battery divided by the potential difference between the terminals, that is 4 pi epsilon naught AB divided by B minus A. Note that this is not the same as the capacitance when the outer shell is given a charge and the inner shell is earthed and no battery is connected. So it does make a difference when you connect a battery. Understood? Again, you must remember this value of capacitance. There you go. Now we'll study a very interesting concept, the concept of a fully charged capacitor. In many IIT JEE problems, the question says, we've connected a battery to a capacitor and the capacitor is fully charged. So what does the term fully charged capacitor mean? Well, it means, when the capacitor has the maximum charge on its plates, the maximum charge that it can have. So what is the maximum value of this charge? Well, the interesting answer is there is no limit to the charge you can add to capacitor plates. The only limit is the potential of the battery. So if we connect a battery of potential difference V to capacitor plates, what will happen is, that the battery will take some charge from one plate of the capacitor and provide the charge to the other plate of the capacitor. So the maximum charge that will come on these two capacitor plates is CV, isn't it? After all, if the capacitance is C and the voltage is V, then the charge on the capacitor plates is CV, isn't it? However, this is not the maximum charge that can come on the capacitor plates. If you put a battery of voltage 10V or 100V or 10 trillion V, then in that case the capacitor plates will get that charge on them. Understood? So basically we can increase the value of potential difference V to calculate the charge on the capacitor plates. Understood? Again, there have been so many concepts that I have discussed in hardly 5-10 minutes. So I know it might sound confusing, but don't worry, persist, keep watching and you'll soon understand everything.